So next we want to consider the arc length function here, s of x. So s is the name of the function and x is your variable. And it's defined by integral from a to x square root 1 plus f prime squared dt, and it's f prime of t. So the t here is taking place of our x variable, and then these are t values here. So t equals a to x, and that's right here. So that's going to give the arc length on that graph from t equal a to t equal x. So let's look at an example here, and we'll kind of get a feel for this. Notice this is just the arc length function rewritten with a dummy variable of integration and a variable upper limit. So we want to find the arc length function, so that's s of x, for y equal natural log, starting from the point 1, 0. So let's get our graph going here. We can see a picture of what's going on. So we got x-axis and y-axis. Natural log function is asymptotic with the y-axis and increasing, crosses at the point 1, 0. And that's going to correspond to t equal 1. So our x coordinate there is 1. So this is t equal 1. And then it's 1 to x. So if we've got a general x coordinate out here, go up to the graph. And the coordinates of that point are x and then natural log of x, because this is the graph of y equal ln x. And then this piece of arc length here, that is s of x. So if x equals 2, it's going to be the arc length from 1 to 2, t equal 1 to t equal 2. If x equals 3, it'll be the arc length from 1 to 3, etc. So what we're doing is we're finding a formula in terms of x, in terms of the ending point, to give that arc length. So let's go ahead and write this out. So s of x is going to be the integral from 1 to x, 1 being the x coordinate of the starting point, square root 1 plus f prime of t. So our function here is, this is our f of x. So that means that if we rewrite that in terms of t, f of t is ln t. So f prime of t is going to be 1 over t. And we've got f prime squared. So 1 over t quantity squared, and then dt. So let's go ahead and simplify here. So integral 1 to x, square root, and this will be 1 plus 1 squared is 1 over t squared dt. And then let's get a common denominator between these. So integral 1 to x, square root, we'll want to write this 1 as t squared over t squared. So multiply top and bottom by t squared. dt. And now we can add the two numerators over the LCD. So this will be integral 1 to x, square root, t squared plus 1 over t squared. So dt. So now we can take square root of the top and the bottom separately. So this will equal integral from 1 to x, square root of t squared plus 1 on top, and then square root of t squared is t in the denominator, dt. So I look at this here and I see a function and almost its derivative here, but the derivative is in the denominator. That's kind of messing things up. But also we've got this square root and we've got sum of squares underneath. So that's suggesting a couple of things. You could try a trig substitution. This looks like, let's see, 1 plus secant squared. 1 plus tangent squared is secant squared. So it looks like tangent squared plus 1. But I'd like to avoid a trig substitution if I could. So how about we look at that numerator and think, well, what if we used a rationalizing U substitution? So what if we wanted to try U is equal to square root t squared plus 1. Then squaring both sides, U squared would be t squared plus 1. And take differential both sides, so 2u du will equal 2t dt. And then cancel the 2's. So u du is t dt. So we've got the dt here. How about we multiply by t on the top and on the bottom? So now we can change this integral over. So on the top, we've got our u. So this will be integral u on the top. And then on the bottom, we've got t times t squared. Okay, well, u squared is t squared plus 1. So that means subtract 1 from both sides. U squared minus 1 is t squared. So u squared minus 1. And then our t dt. So this is our t squared, which is u squared minus 1. And our t dt is u du. And then we have to change our limits over. So take the 1, plug it in here. So that'll be square root of 2. And then take the x and plug it in here. So that'll be square root x squared plus 1. So let's go ahead and rewrite here. So this is going to equal integral from root 2 up to square root x squared plus 1. In the numerator, we've got u times u squared. And then denominator, u squared minus 1. And then du. So we got rid of the square roots, so that's nice. And now this is polynomial divided by polynomial, so that's looking like partial fractions. So we want to do a long division here. So we've got u squared minus 1 dividing into u squared plus 0 if you want. So you divide your leading coefficients. U squared divided by u squared is 1. So 1 times u squared minus 1. We are subtracting that. So change the signs and add. These guys cancel. We get a 1. So this will be plus 1 over u squared minus 1. So we're really integrating from root 2 to root x squared plus 1. And then this is going to be 1 plus 1 over u squared minus 1 du. And then we can do partial fractions on that part. So let's see here. We've got 1 over u squared minus 1 is u plus 1, u minus 1. And the partial fraction decomposition is going to be a number over u plus 1 plus a number over u minus 1. So we multiply through by the LCD, which is u plus 1, u minus 1, both sides. So u plus 1s, u minus 1s cancel. We're left with a 1 on the left-hand side. Right-hand side, we're going to multiply these in. So in the first term, the u plus 1s cancel. We are left with a times u minus 1. In the second term here, the u minus 1s cancel. So we're left with b times u plus 1. So now we can use undetermined coefficients. So pick some values here of u, and we want to pick our denominators. So if u is equal to 1, we get 1 equals, here 1 minus 1 will be 0. That first term drops out. 1 plus 1 is 2, 2b. So our b is 1/2. U is equal to -1 is the other 0 for denominator. That'll give negative, it'll give 1 equals -1 minus 1, -2a. And then -1 plus 1, the b term cancels out. So that'll be a is -1/2. So now we can go ahead and rewrite this. This will be integral from root 2 to root x squared plus 1. And then 1 plus, and in place of that 1 over u squared minus 1, we're going to do a over u plus 1. So -1/2, and then b over u minus 1, 1/2. Let's put the b term first. So b over u minus 1, so 1/2 over u minus 1, and then plus a over u plus 1, and our a is -1/2, so -1/2 over u plus 1 du. And now this is easy to integrate. We're almost there. So antiderivative of 1 is just u. Bring the 1/2 out in front. And then you'll have left a 1 over u minus 1. That looks like g prime over g. Antiderivative of g prime over g is natural log of g, right? If you've got g prime over g and you integrate that, you get natural log absolute value of g. So I'm going to get ln absolute value u minus 1. And then minus, again, bring the 1/2 out in front. And then again, times 1. So we get g prime over g. So ln absolute value of u plus 1. So there's our antiderivative. And we are going to evaluate that from root 2 root 2 on the bottom up to root x squared plus 1. So now we just have to do our plugins. Well, actually here we could do a little bit more to simplify here. Subtraction here outside the logs is division inside. So you get that common 1/2 that we can factor out. This is actually going to be u plus 1/2 comes out. And then we've got log u minus 1 minus log u plus 1. So that'll be ln absolute value. Division inside is subtraction outside. So u minus 1 over u plus 1. So that'll be a little bit easier to do our substitution. Root 2 to root x squared plus 1. So now we're just plugging in. So we get root 2, root x squared plus 1 in for u there. plus 1/2 natural log, and then root x squared plus 1 in both places there. So root x squared plus 1 minus 1 over root x squared plus 1 absolute value, and then that whole thing minus, now we're plugging in the root 2. So root 2 plus 1/2 natural log. And then on top, we won't need the absolute values here because everything will be positive. Root 2 minus 1 over root 2 plus 1. So now any x value that you give me, I can just plug it in here, and then I'll have an exact value for the arc length starting at x equal 1 and going up to that variable x. So quite a bit of work, and these arc length functions, when you actually find the arc length function s of x, that is usually quite a bit of work. Sometimes multiple methods are needed. So this is our s of x. So probably not a test question here because it's just got too much going on, too messy. But I wanted to see, one complete arc length function, and this for an easy function, log x. Not real crazy, not anything real crazy going on. Well, the integral looks kind of crazy, doesn't it, with a couple methods there.